did you know that the doctor who invented lobotomy, the surgical practice of removing half the brain, got a Nobel Prize for this?
Why? Because he removed the brains of Nobel Prize committee or what?
Sounds like that, but in those days, this was actually considered a revolutionary great medical treatment.
What?
Okay? In 1951, 20,000 people were lobotomized in the US. Okay? And it turns out mostly gay people to cure them of gayness or women. Okay?
Ouch.
So, how does this happen? How does the entire world look at a barbaric practice like this and think it is a Nobel Prize winning level discovery, right?
My question exactly. How does this happen? Didn't they see that removing the brain basically reduced them to a state of childlike behavior?
Well, I mean, one issue is that in some cases they think childlike behavior is better than whatever was before. More importantly, there were many cases in which it didn't actually work well, and those just got conveniently ignored because you want to focus on the ones that worked. Okay.
Ouch.
So human beings are pretty terrible at getting a good feel for whether something is working or not. And that is why randomized controlled trials, which solve this problem, are one of the greatest inventions of the 20th century. Okay. And with National Science Day coming up, we thought we will talk about RCTs today.
Makes absolute sense. All right. Tell me about randomized controlled trials then.
Before that, let me give a better example of why we need randomized controlled trials.
I think lobotomy was a pretty good example by itself.
Well, not really, right? I mean, a lot of people think, oh, maybe they deserved it and all of that, right? And because it happened just to like a marginalized community.
Yeah.
Let's take a more mainstream example.
Okay.
Bloodletting. For thousands of years, there was a medical procedure called bloodletting where you actually make a hole in the person and take out blood, like liters of blood.
Yeah.
And that is supposed to cure you of diseases. Why? Because the theory in those days was that diseases are caused by bad humors which are in your blood. And if you remove the blood, now you have less bad humor. Okay?
You also have less blood, and when you have less equal to 0, then you have no blood and you die.
So you're trying to make a joke, but really, okay. So how mainstream was this practice? Okay. George Washington, he had a throat infection and his doctor suggested bloodletting, and over a period of 10 hours, they let 3.75 liters of his blood and he died.
Of course he died. The human body has 5 liters of blood. You take 75% out of it, the person is going to die. My question is how did they not test and verify it? How was there no record keeping of whether bloodletting worked or not?
Okay, so here is a question, right? What do you define as bloodletting worked or not?
Well, the person lives and gets healthy after bloodletting.
Yeah. So what happens? Most likely what happened in a lot of those cases is that you say collect statistics about you used bloodletting and did people get better, and you see, oh, majority of the people did get better.
So bloodletting works?
No. What it means is that a majority of people get better for any condition, whether you do anything or not. Right?
True.
This is called the ad hoc fallacy. That's a Latin phrase. The full phrase is ad hoc ergo propter hoc, meaning after this, therefore because of this.
Correct.
If something happened after something else, you assume that this something happened because of something else.
Correct.
Right? And Tolstoy has a great quote about this, right? What he says is that if you have a medical problem and you are given some treatment to make that problem better, and then if you actually get better, no power on earth can convince you that you didn't get better because of the medicine, right?
Yes, and we've seen this in a lot of cases, and we always talk about homeopathy in this context, so I'm not even going to bring it up now. Go on.
The thing is that why somebody got better could be so many different things, right? Everyone is trying various different things and one of them worked and you don't know which one, right?
Correct.
Let's take another lovely example.
Okay.
Scurvy. Okay. So scurvy is this disease that used to affect only sailors.
I remember in school we learned scurvy happens due to deficiency of vitamin C.
Right. Oh, you gave away the answer. But yeah, sailors used to die on long voyages after getting a disease called scurvy. Okay. And nobody knew what is causing it. Nobody knew how to fix it. Okay. Over the centuries, people had tried all kinds of remedies for this. Okay. And you know how people are, right? They get attached to remedies. And some people would swear by this remedy and somebody would swear by a different remedy, right?
True.
There was a guy called James Lind who decided to look into this in detail.
Okay.
He studied centuries of reports about various remedies and he just saw that there is just, too much going on here. But he felt that citrus fruits probably do cure scurvy. Okay. But he didn't want to just get attached to it. Okay. He had a scientific mind. So he came up with an experiment to find out.
Okay.
On a ship, he divided sailors into two groups. And one group, he gave them lemons.
Okay.
And the other group, he did not give lemons. And at the end of the voyage, he saw that the ones who were given lemons did not get scurvy while the others did.
Yeah, because their vitamin C deficiency was covered by the lemons.
They didn't know anything about vitamin C and deficiency, right?
True.
All he knew was that giving lemons to this group seems to work.
Right.
And he knew this with a high degree of confidence because he had separated them out into two groups. One group got the treatment and didn't get scurvy. The other group didn't get the treatment and got scurvy, right? So clearly the difference in the two is the treatment, right?
All right.
So this is called a controlled trial. Okay. This group is called the treatment group. And this group, which didn't get the treatment, is the control.
So you divide them into two groups. One gets the treatment, one does not get the treatment.
Right. But there is a twist.
Okay.
Over the years, people have discovered a new problem.
Okay.
For example, if you do an experiment like this, this group doesn't get treatment. This group is given treatment. They are told that they are being given a medicine, but in reality, they are just given sugar water.
Okay.
What do you think will happen?
It should not work, right? Because it's not the treatment.
Unfortunately, almost all over the world, this group actually shows better results than this group.
What? Why?
We don't know for sure. Okay, this is called the placebo effect.
Acha.
And as far as I understand it, this is because human body is a wonderful thing, right?
True.
If you are giving treatment to some people, it makes them feel good about themselves. They think that, yes, I can do it now. And as a result, their immune system works harder. Whereas if you give people something saying, you know what, this is going to make you worse, they actually get worse because their immune system gives up. It says, oh, well, already I was in trouble and now you are giving me some horrible thing that will make me worse, and they get worse. This is, by the way, called a nocebo, which is the opposite of a placebo. But in any case, the point is that just by manipulating your emotions, you can make people better. Okay? This has been proved again and again and again. So, the point is that in modern science, you can't have two groups where one is given the treatment and one isn't. What you need is two groups where one group is given the treatment and the other group is given something which they think is a treatment, but they don't know that they are just getting something which is
a placebo.
blank.
Yeah. Okay, because you have to have a treatment that works better than the placebo.
Exactly.
Because if the treatment works as good as the placebo, then it's not a treatment at all.
Exactly. Yes.
Okay. But here's the question. What if the group that is getting the placebo is already healthy? As in, they don't, they are good enough to recover by themselves.
Yes. So that's the next problem that you need to solve. Okay. Because sure, I mean, you take one group who's getting the treatment and the other group just happen to be a group that is healthier or going to get better.
Yeah.
Then you haven't proved anything, right?
Correct.
So what you have to do is you have to make sure that the two groups that you have, the only difference between the two groups is that one is getting the treatment, the other is getting the placebo. All else has to be equal. So for example, you can't do this experiment where the sailors on one ship get lemons and the sailors on a different ship don't get lemons, right? Because you never know, that ship is different, the food on that ship is different, the captain treats them differently, their sleeping schedule is different, any of these things could affect it, right? So you have to do it with all else being equal.
Right. So it had to be the same ship. It had to be from the same bunch of sailors who shared the same routine every single day. That is why the controls also needed to be equal to the treatment in these two groups.
Yeah.
But how do you achieve this equality? Because everybody is different, everybody has a different constitution, everybody has a different health trajectory, or whatever you want to call it.
Let me give you a story of how that came about, right?
Okay.
So in the early 1900s, Ronald Fisher, a great statistician, he was studying agriculture. Okay. And farmers were all very confused about various agricultural policies, right? Which fertilizer works well or doesn't, what crop rotation method is good or not good, right? The problem is that every farm is so different, and even for the same farm, every year is so different, right? So how do you get any idea of control, right?
Yeah.
I mean, oh, you used fertilizer this year and everything is good, but that could just be because the weather was good this year, right?
Or the rains were good this year.
How can you do this?
Yeah.
Okay. So Fisher, who was a statistician, came up with a brilliant idea. What he said, take a large enough group, okay? And then you randomly assign half of them to the treatment and half of them to the placebo, right? Now, if you did true randomness, right? And the numbers are large enough, then whatever are all the individual difference between them should cancel out roughly, and they should all be more or less the same. That's the idea of randomness, right?
Yes.
And then you give one of them the treatment. So this is a very, very clear difference between these two groups. Everything else being random, all else is going to be equal on an average.
Correct.
Across the group, right? Of course, some will be up here, some will be down here, but the same will be true of this group also.
And on an average for the entire group of both groups, it will cancel out and you'll get like a statistical mean kind of a thing.
Correct.
Wow.
But still, this whole thing put together didn't happen until 1948. 1948 is the first scientific paper about streptomycin, which talked about randomized controlled trial.
Interesting, because you told us that the Nobel Prize for lobotomy was awarded in 1949.
Yeah.
The RCT for streptomycin happened in 1948. If the RCT had extended to the lobotomy practice, then maybe the Nobel Prize would not have been awarded to lobotomy that year.
Absolutely, right?
Yeah.
Because since then, RCTs have become so important that we pretty much try to use RCTs for any important discovery.
So what I'm taking away from this is that RCTs were invented to solve the placebo effect, and they did.
They did, but in fact they solved other important problems. Okay, there are three major problems: selection bias, confounders, and observer bias.
Okay.
And RCTs solve those also.
Okay, what are these? Let's take them one by one. First, selection bias.
So there is this great study called the Illinois Workplace Wellness Study. Okay. So work wellness programs were offered to employees. Okay. And the program offered activities like weight loss, exercise, Tai Chi, smoking cessation program, financial wellness program, and all of this, right?
Sounds like a great workplace.
And then they looked at people who did this program versus people who didn't do the program. And the question they asked at the end of the period, what was the difference in behavior, difference in outcomes?
Correct.
Okay. So the people who took the program went to gym at double the rate of the people who didn't. Okay. The people who took the program ended up spending $525 on an average on healthcare. Compared to $657 for the people who didn't. So healthcare cost has gone down.
Correct.
Hospital related costs went down from $387 to $273. Right?
Okay.
Not just that, but people who took this activity only 7.2% of them quit their job, whereas attrition in the other group was 15%, right? So attrition also halved.
So this sounds like a great workplace wellness program. Why didn't it work out? What was the problem?
Selection bias, right? I said that this program was offered to employees.
Oh.
They chose whether to be in the program or not. Now you tell me, who takes a wellness program? People who already wanted to go to the gym joined this program. Okay.
Yeah.
Now, why did I say this was a great study? Okay.
Yeah, why did you say it was a great study? Because it seems not.
They picked 5,000 employees
Ah.
and then they offered this program only to 3,300 of them. Okay.
Acha.
About half of that 3,300 took the program.
Huh?
The other half who were offered didn't take the program, but there were still 1,700 people who were not offered the program at all.
Okay.
Now, the 1,700 who were not offered the program at all,
Huh.
if you compare those
Outcomes.
those outcomes to the outcome of this whole group,
Huh?
no difference. All those differences that we saw disappeared.
Yeah,
Right?
because the control here was not the people who took the program or didn't take the program. The control here was the people who were offered and not offered.
Exactly. And
Acha.
that they had done randomly. And that was the only way to get all else being equal. Because in this group, which were offered, all else was not equal.
Correct.
Right? In fact, all else was different because the ones who picked were very different from the ones who didn't pick.
Yeah.
Right? And that proves why you need randomization in your control trial. And what it also means is that selection of that group is very, very important to do randomly, because humans, no matter what they do, if you pick based on some criteria, you are going to introduce bias of some sort.
Correct. So randomization makes sure that that bias of selection doesn't exist.
Yes.
That explains selection bias. But then you also said confounders, right?
Yeah, correct. So
What
that's
are the-
another very important concept. So let's take this example, okay?
Okay.
They did a study and they found that people who have coffee get lung cancer at a higher rate.
But liver doctor keeps saying coffee is good. Have 3 cups of coffee every day. He says black coffee.
Well, so yeah, coffee is not bad. So how do you explain the fact that it looks like, people who drink coffee are getting lung cancer? When you look closely, what you notice is that people who like to smoke also drink coffee at a higher rate and they get lung cancer at a higher rate. So if you don't pay attention to the smoking, it will look like extra coffee consumption is causing lung cancer. I'll give you a simpler, funnier example, right?
Please.
If you look at the data, you will see that increased ice cream consumption increases drownings.
Yeah, I'm beginning to remember this now.
Yes. So the confounder there is the fact that in summer, when the heat goes up, ice cream consumption increases, swimming also increases. That is what is causing drowning, right?
Yeah.
So the idea of a confounder is a common thing that explains both the variables you are studying. We have done an entire episode on this. Check it out. It's excellent stuff. You can go into a lot of detail there.
Yeah, the episode is called Correlation is Not Causation. And we've taken a lot of these examples, not just confounding variables, but we also talked about something called spurious correlations, which is really funny. And I'll tell you why it's funny, because pirates cause global warming. If you want to know why, go check that episode out. But that explains confounders.
Yeah.
The third one is observer bias, you said?
Yes, that's a very important one.
Okay.
Humans are terrible at observations. Okay. In fact, I keep saying believing is seeing.
Yeah.
So just your beliefs completely color what you see, what you record, and that makes a huge, huge difference in experiments, right?
True.
We already talked about one of those things.
Yeah.
When the patient believes that they are getting treatment, their outcomes improve. Okay?
Placebo effect.
But similar problems exist with the researchers, right?
Oh, okay.
So let me take an example. Okay. Imagine I told you that there is a horse here which can count, and there is a horse there which can't count. Okay. And the way this horse can count is that if you hold up a sign with, say, 5 plus 2 written on it, the horse will tap his foot 7 times.
Wow.
Okay.
Smart.
Yeah. This is a real horse called Clever Hans.
Okay.
Now, if I told you this and I told you to go and observe whether it is counting or not, and you also go and observe this horse whether it is counting or not, you know what will happen if I did that with a number of experimenters? Very likely that you will get back results, at least from some of the experimenters, saying that this horse can count and this cannot.
But he can count, right? Like if you hold 5...
No. Clever Hans was a horse who was so clever.
Okay.
The horse didn't understand numbers. What the horse understood was that you keep tapping your leg until people start clapping.
That's clever.
Right. So the problem is that the observers, they already believed that this horse can count. So they were just waiting for him to reach the correct number and they would start clapping. Okay. Right. And this also kind of happens in real experiments, right?
Achha.
When a doctor believes that this patient is being given this strong medicine, that I'm being forced to do an RCT because of FDA laws, right? When the doctor believes that, the doctor behaves with the patient differently, takes observations differently. If the patient is doing a little worse, they say, no, this is some temporary thing, so I might not record it. And all kinds of problems occur because of that.
Yeah, that makes sense. So what you're saying is RCTs don't fully solve observer bias.
Yes, you have to add one layer to the RCTs called double blind.
Double blind.
So we already talked about how the patients don't know whether they are in the control group or the treatment group.
Right.
Similarly, the researchers should also not know who is in the control group and who is in the treatment group, right? So for example, during COVID, when we were trying to figure out whether the vaccine works or not, half the people were being given like a generic thing and half the people were being given the vaccine, and the doctors giving that didn't know which was which. Right? That is called double blind.
So both of them are blind.
Correct. The patient is blind and the doctor is also blind.
Right. So what I'm taking away from this is that RCTs with double blind is the gold standard. But my question is all science done this way now?
No.
Okay.
I'll give you an example.
Okay.
Parachutes don't work.
But they do work.
There has never been an RCT proving that parachutes work, which means that it could just be like bloodletting, that we are all just, mistaken about this.
There is enough evidence. Plenty of people have taken parachutes, jumped out of a plane, pulled the cord, and their parachutes have opened.
And I'm assuming that this is your treatment arm, and there is a separate control arm where people are jumping out with placebo parachutes.
What even is a placebo? Okay.
Now you see why you cannot have an RCT for parachutes.
Yeah.
This brings up ethical questions, right?
Yes.
In more gray cases, right? Imagine that there is a drug which in early trials has shown that it cures a particular disease.
Yeah.
And now you're doing a larger trial. So you take a bunch of people who are going to die and you say, well, we are going to flip a coin to decide which ones of you get the medicine that will probably save your life and which ones of you we are just going to let you die.
Yeah.
Right. So there is a issue.
There is that ethical issue for sure. So yeah, RCTs with double blind are a good measure, a gold standard, but they are not the ultimate solution is what you're trying to say.
But wherever possible, you should use RCTs. But sometimes it is not applicable. Sometimes it's a little too heavyweight. But mainly I want you to take away from this episode the reason why RCTs had to be invented. Without RCTs, there were those problems: placebo effect, observer bias, confounder, selection bias. Those happen not just in those science experiments, they happen in our life all the time. And we need to learn to spot them and to be able to solve them using RCT-ish techniques.
Yeah, and as you were mentioning all of those examples, I realized that there is a lot of things in our day-to-day life where those problems crop up. Like placebo effect we've seen very regularly in cases of homeopathy. And then that Tolstoy quote comes to mind, which is why homeopathy works, I guess. But then selection bias, for example, a restaurant sends out an online survey asking what people thought of it. But online surveys are typically answered only by the young people. The older people are not going to sit filling out online surveys. So their opinions are not considered in the reputation of the restaurant.
Yes.
We spoke a lot about spurious correlations and confounder effects. We've done an entire episode on it. Observer bias, where do we see observer?
Well, all of politics is observer bias, right? The same thing a leader does. Half the people think it is the worst thing ever done, and half the people think it's like the best ever done, right? I will give you another lovely example, right?
Please.
Astrology, all of astrology works through observer bias, right?
Yeah.
And it is called the Barnum effect. We have done an entire episode on it, which you will love. If you liked this episode, check it out.
Yeah, we started off talking about RCTs considering that National Science Day was coming up soon, but then it's not just about RCTs, it's about why those RCTs came into existence, and all of those problems that the RCTs solved are also problems we experience in our day-to-day lives, which is why I hope you've taken all of these things into account and you've started thinking about your life in terms of these issues. And try and figure out how you can apply RCTs in your own life. Let us know what you did. Meanwhile, this is Srikanth, Naveen, FutureIQ.